Welcome to my channel. This video is going to discuss asymmetric dielectric slab waveguides. Basically, like all kind of slab waveguides, we have the right derivative being equal to 0, and similar to symmetric dielectric slab waveguides, we have altogether 3 layers. But the upper dielectric layers and the lower dielectric layers are of different refractive index. The style of analysis will be more or less the same. It's based on the Maxwell equations for the in almost exactly the same manner. Yeah. But during our model analysis, we cannot split the modes into odd modes or even modes. The asymmetric nature of the waveguides can be used to our advantage to simplify the model analysis. So to start with, I'm going to show you the cross-sectional view of this asymmetric dielectric slab waveguides. Basically, it is a sandwich of 3 layers, with the middle layers as a core. The core has a refractive index n of 1. The thickness of the core is d, and the bottom layers is the substrate layer. It has a refractive index n of 2. The upper layers is the cladding layers. It has a refractive index n of 3. The interface for the bottom for the core and substrate is going to be in at x equals to 0. The upper interface, the interface between the cladding and the core will be at x equals to d. And as before, we are going to use the z direction as a direction of propagation. The vertical direction is going to be the direction of x. Another invisible direction is the y direction. The y direction is the direction into or out of the screen. Now let's take a look. In a symmetric waveguide, we have the V number. We also have the V number for the asymmetric dielectric slab waveguides, but the V number will be defined for the interface between the core and substrate. As a result, the V number is going to be equal to this one. So what about the interface between the cladding layer and the core? This will be dealt with by another parameter known as asymmetry factors. Now, take a look in the pathway of electromagnetic wave, so-called the light. The light can travel from A to B in a non-vertical directions, and once hitting the interface at B, you will get refracted, forming a pathway BC. And because of the law of reflection, we expect the angle of incidence being equal to the angle of refractions. And this is how we end up with the so-called total internal refractions. Now, when the lights go through the pathway A and B, it will undergo the phase difference K times cosine beta of 1. Yeah. K is equal to N1 times K0. And similarly, the light going through the pathway B and C will also undergo another phase difference given by N1 times K0 times cosine of beta 1. And on the other hand, when the light hits the upper interface, it will undergo another phase change. 2V3 and 2V2, right? I got it wrong here. It should be V of 2. Yeah. So altogether, the total phase difference will become this much. So the round trip has a phase difference 2 times n of 1 times k0 times cosine of v beta 1 plus 2v2 plus 2vp. And in order to have a successful total internal refractions, we have to make sure delta v is equal to 2m pi, 2 times the integer multiple of pi. And in the analysis that follows, we are going to use Maxwell equation to derive this one first, and then we are going to analyze the Maxwell equation. So the Maxwell equation, the analysis using the Maxwell equation is so-called the modal analysis. We are going to start with the amplitude wave in the y direction. And if we want to understand why we need to do that, then I suggest you take a look in my YouTube video on Asymmetric Dielectric Slab Waveguides. So before advancing further, let's develop some prerequisite concept first. So let's take a look. Let's assume the electric field in the y direction is given as this much, right? The amplitude times the exponential term. The argument of the exponential terms will be the phase, time dependent phase, and positional dependence phase. If we differentiate equation 1 of 1a with respect to time, we will get this one. And as a result, we can assume all the time derivative operators is equal to j omega in phasor form. And similarly, if we differentiate equation 1a with respect to z twice, we will get this one. K of z squared times e of y. And as a result, all the second derivatives of z operator we will replace it with minus k of z squared. And finally, I have to remind you, the k vector can be written as k0 times n of I, where n of I is the reflective index of layer I. So we are going to start with our analysis with the wave equation for the amplitude E of y. And then if we explain this equation, we will get this. And if we expand the expression of k, we will get this one. Where n of I here is the refractive index or layer I. And because all the y derivatives have to be zeroed, so we can minimize this term, delete this term from the equation. We get this much simplified one. And if we rearrange this equation, we will get a second order one-dimensional equation of this one. And remember, the bracketed expression on the right side is k of x squared. So the core, we expect the wave to be guided in the core. For the wave to be guided successfully in the core, k of x has to be real. This means k1 times k0 has to be greater than kz in the previous equations. And the bracket expression is just k of x squared. And kx has to be real in order for the wave to be successfully guided. So the solution to this differential equation is going to be that simple: a times cosine this term and plus b times sine of this term. In the substrate, we don't want any wave to be present. So we want the wave to be evanescent. This means that we want the wave to be decaying. To be able to do that, we have to make sure this term is imaginary rather than real. So we have to make sure k of z is larger than kn of 1, n of 1 times k0. And these terms is going to be minus of alpha 2 square. The solution to the core is expected to be of this form. Is a non-sinusoidal expression. Is decaying with the attenuation constant alpha of 2, where 2 stands for the index of the substrate. So similarly, for the cladding, we are going to have the similar treatment as those for the substrate. The refractive index of the cladding is n of 3. There will not be any standing wave, and the wave will be decaying until it completely vanishes. So, like what we have done before, right, k of z has to be greater than n of 3 times k0. So in this case, we expected the solution to equation phi a to be of this form, where alpha for free will be the attenuation constant for the cladding. Sorry, I make it wrong here. Here should be alpha of free. So medium free. So altogether, right, we have this set of solutions. The longitudinal magnetic field associated with the transverse electric fields can be obtained using the Faraday's law, using this equation, and this will be the derivative of E of y times this vector. Yeah. So if we differentiate this term, this equation P of A, we will get this one, and if we differentiate equation 4A, we will get this one. If we differentiate equation 4 5B, we get this one. So now we are going to use these relations to we are going to apply the boundary condition for these relations. So first of all, we are going to deal with the boundary condition for the core and substrate interface first. This means we are going to substitute x is equal to 0 first. And then we are going to deal with the boundary condition for the upper interface, where x is equal to d. So let's take a look in these slides. So first of all, let me tell you the ultimate objective of this step. We are going to substitute the boundary condition, and then the next thing that we need to do is to eliminate all these ABCD constants. So at x is equal to 0, what we are going to obtain is d is equal to a. At x is equal to d, we are going to end up with the this expression for d, because cosine of this term is log 0, where sine of this term is log 0. So now, what we are going to do is we simplify we are going to apply the boundary conditions for by substituting a equals to d. And as a result, we got this equation. Yeah. And then if we rewrite this equation, we are going to get b equals to this one. And we are going to apply the boundary condition for the upper interface again for the magnetic field, tangential magnetic field. And we will get this. And if we substitute b with this expression into equation 10, we are going to get this. So b can be rewritten as this one. Sorry, if we substitute b for equation a, we will get this one. And if we substitute the expression for b into equation 10, which is the equation for the tangential magnetic field for the upper boundary. We are going to get this. Now, the trick here is we are going to eliminate the constant A and C. The only way to eliminate the constant A and C is to find the ratio which divides equation 12 by equation 11. We find the ratio of these two equations. So here we go. We get this. The final equation is without any ABCD constant. On the right side of the equation, we are going to divide the top and bottom by cosine x d. So we get this. Now what we are going to do is to apply the Finot's theorems for this alpha 2 divided by kx, k2, kx, alpha 3 divided by kx. Actually, the tangent of this, remember, right? The tangent of refractive index is going to be the phase during the refractions. The tangent of the refractive index ratio is going to be the phase difference during the refraction. So for the upper boundary, we have this one, and this one. I should say the arctangent, I make assessed incorrectly in the previous equation, So we have this expression, and we substitute this into equation 14. We will get this one. And the right side of the equation can be substituted with another trigonometric identity, k of x times d minus v2. So if both tangents expressions is equal, if both tangents expressions are equal, then their arguments should be equals as well. So we get by equating the argument of this equation, we get this. Because we have to make the case general, so we have to add m pi here. So finally, this is the equation for the characteristic equation. We got this equation, We have to make sure the left side of the equation is equal to m pi, and if we substitute v2 and v with the expressions from here, we get this one. M stands for the mole number, m1 m equals to 0, 1, 2, etc. So the final solution is going to be very simple. It will be based on equation 15. So what we are going to do next is to replace this term with an expression in terms of V and B. And we are going to do the same for this term and replacing this with an expressions in terms of B. And this term we are going to do the same, expressing this expression in terms of B. But we need to do a little bit of adjustment because this is the upper interface. This is the phase difference. Due to the upper interface, we need to asymmetry factor to handle this drop. So B, let's define another parameter B. This parameter is called normalized propagation constant. The normalized propagation constant is the effective guide refractive index square minus n2 square and then divided by n1 square minus n2 square. The n of EFF is the refractive index, effective index given by this term. I should say K here, it shouldn't be K naught. So I make another mistake. Kz divided by K, yeah. So as a result, I should say is n of K. Yeah, I missed the n of here. So as a result, we will get this one. So we are going to substitute. We are going to use this expression advantageously to simplify equation 15. Each term in the equation 15 can be simplified. And also, we need to know that the normalized frequency of V number is given by this one. This formula is universal. And remember, D is the thickness. So let's simplify the leftmost terms of equation 15, kx of D, which is equal to this one, and which is equal to plus or minus this term. So it's not going to affect the value inside the square root. So with a little bit of rearrangement, we get this. Yeah, we move this term to the second position, we get this. And if we divide the top and bottom of the square root term with this factor, and move this to the front, and we get this one. So if you take a look here, this expression is just the number V number, and this one divided by this one is going to be 1, and the rightmost bracket expression on the numerator divided by the denominator. We are going to get b. So the whole expression for kx times d is given by v times square root of 1 minus b. And similarly, we are going to express alpha 2 divided by kx. And again, we are going to use the formula for alpha 2, which is this one, square root of very complicated expression. And the bottom, the formula for kx is this one. So what we are going to do is to plus and minus k log square times kn2 square. Is not going to affect the value of the bottom expression. So do a little bit of rearrangement and divide the top expression, the top and bottom, with the square root of this term. You get this one. And if you take a look at this one, it's actually equal to 1 over b. And we just do a little bit of algebraic rearrangement. We will get this one. So this is going to be equation 19. And finally, we are going to simplify alpha 3 divided by kx. And we go through the similar procedure. And we add the top and bottom with k log square n2 square and minus k log square times n2 square. So we are not going to affect the value of the top expression and the bottom expression. It will stay the same. And the next thing we are going to do is to move the this term k log minus k log square and n2 square to the second. And we got this one. And if we divide the top and bottom with this term, we got this one. So finally, we have got a similar expression like what we did for alpha 2 divided by kx, with the only exception here. We get one more term here. So what we are going to do is to use plus a to define this term. A represents the asymmetry factor. And asymmetry factors is going to be like this for TE mode. For TM mode, we have to go through the similar analysis as we did for TM mode. It's a time-consuming procedure. But the final result will be very similar, with the only exception on the value of A, the asymmetry factor. For TM modes, the asymmetry factors is going to be addressed by multiplying this factor, bracket n1 divided by n3, and then to the power 4 and times the original one. So in summary, we start with the solution, characteristic solution, equation 15, and if we substitute all these terms with alternative expressions, we got this one. And this equation 2, will be the ones to be used for all the waveguide problems for modal analysis. The asymmetry factors here will be divided into two forms, one for the TE modes, another for the TM modes. And the normalized propagation coefficient constant for TE modes and TM modes as well. So I missed this term. Will be given by this one, this equation. And we have also developed the formula. We are going to use the universal formula for the B number. And this is so-called the normalized frequency. The reason why we call this normalized frequency is because this expression is going to use the cutoff frequency. So the next thing that we are going to do is to plot equation 22. It's very easy, right? We plot we move the terms to the right and then divided by 1 minus b, yeah, square root of 1 minus b. So we are going to plot equation 22. So this is what we are going to get. And I'm going to briefly describe how this equation look like. Basically, you have got multiple modes associated with each mode is a family of curves for different asymmetry vector. So in here, right, A is equal to 0, A is equal to 1, A is equal to 10, A is equal to 100, right? Similarly, right, for M mode 1, we got the same. And this M mode vector can be applicable to TE mode and TM mode as well. This is the equation. It is not based on any physical parameters. So as a result, because the graph here is not based on any physical parameter, it is just the equation 22. It should be applicable to all conditions, TE mode or TM mode, the same here. And to be able to use it, what we need to do is to draw the vertical line representing the value of V number. And the next thing is to find the intersection points for B. With the value of B, we should be able to find the cutoff frequency and propagation constant, and also the permitted mode numbers. So I've given you the Matlab equations, the Matlab program for plotting the BV graph. It's very simple. It's not based on any physical parameter of the waveguide. I don't use any refractive index here. I don't use any thickness here or frequency. And now let's take a look in the cutoff. So let's go back to the to the graph. When are we going to have cutoff? Cutoff represents the condition where alpha is starting to be positive and real. So the starting value of alpha is when b is 0. B is 0 represents the condition where the wave numbers of the propagation mode in the direction of propagation is going to be the same as the reflected the k number, the propagation constant for the surrounding material. This is the condition of unguided mode. So what we're going to do is to find the crossover point in the horizontal axis, and from there we find the cutoff wave number, cutoff wavelength. So cutoff start to occur when alpha is 0 and then positive. So the starting point is alpha 2 is equal to 0. This is the condition where n of z square is equal to this one, is equal to the surrounding material. And similarly, we can get a similar cutoff condition for the substrate and for the cladding separately. Under the unguided condition, the wave number of the surrounding material is equal to the wave number of the propagating mode. So the next thing that we need to know is if we reduce the thickness of the core, when under what condition the cutoff is going to happen. So we are going to find out which one comes first, because the loss in the substrate is going to be much larger than the loss in the cladding. So in this case, we have to determine that the cutoff is going to occur in the substrate core interface first. The next thing that we need to focus on is alpha of 2. This is going to give us the first cutoff. So we equate the B number to 0. And the B number is already given. The B number only relates to the core and substrate. And by substituting B equals to 0 here to equation 22, then we simplify this into this equation. Equation 22. I should have written it down. So this is going to be the formula for the cutoff. V here is V of C, the cutoff V number. So remember, V of C is going to be equal to this one. And remember, A is different for TE mode and TM modes. So in other words, the V number for the V of C for cutoff for TE mode and TM modes are going to be different. So let's do a little bit of substitution for K0. We get this one, and lambda of M here represents the cutoff wavelength. So as a result, we get the cutoff frequency for a particular mode. Now the thing is, if we decrease the core thickness, we need to and then what is going to happen for the cutoff? So first of all, we need to know the first cutoff condition. The first cutoff condition always occurs when in the TM modes, because when the thickness of the core is reduced. If we want to know the first cutoff, then we need to find the largest value of the right side of the equation. And the largest value in the right side is when A is largest. A is largest when in TMOs. Yeah. The asymmetry factor is going to be larger for TMOs. So if the thickness is to be reduced, then the higher order TMOs will be cut off first. So let's take a look in this example. In this example, the waveguide parameters are given, and the wavelength is 1 microns, and the thickness of the waveguide is 1 microns. So we are going to find the B numbers. The second part of the equation is to find the asymmetry factor for TMOs and TEMOs. And we are going to verify that two guided conditions. We have only two guided TEMOs and TMOs. And I think the easiest thing is to use graphical means to verify it. And finally, we are going to find the propagation constant of all the guided modes. And the final part of the question, we are going to reduce the thickness of the guiding layer. Which of these four modes is going to cut off first? So if we recall what we have done for the cutoff section of this slide, we know that it will be the substrate that use the cutoff first, and it will be the TM mode that use the cutoff first. So and also the highest mode number will generate the cutoff first. Yeah, let's take a look. The V number is going to be like this. Well, really easy. The asymmetry factor can be obtained using this formula, and the asymmetry factor is going to be 1. The asymmetry factors for TM modes is going to be larger because of this term. According to our calculation, is 10. And to prove that uh, there are two guide modes for TE modes and two guide modes for TM modes, we can either solve the transcendental equation given in equation 22 numerically or graphically. Let's see the graph in overlay. So this is the universal PV part. What we need to do next is to add the vertical line representing the V numbers. And then from there we find the intersection points according to the asymmetry factor. Now let's take a look. Remember the asymmetry factor for TE modes is 1. So we are going to pick the second curve because the second curve represents the asymmetry factor as 1. Similarly, for the second family of curves, we are going to do the same. And we are going to find the intersection point first. So for TE0 mode, we got this. And we know the V number there is 0.85. For m equal to 1, we need to take out the intersection point from the second family of curves. We got this number. The V number for TE1 is the B for TE1 is 0.42, and for TE box we got the solution. We can work out all the parameters according to these two numbers. But for the TM modes, the asymmetry factors is going to be different. So with the asymmetry factor, remember the asymmetry factor is 10, approximately 10. So we are going to pick the third curve within each family of the curves. And according to our analysis, the intersection point where the vertical line and the third curve intersect is going to yield B is equal to 0.83, and similarly we can do that for second mode. So the B value, the value of B normalized propagation constant can be found for all. All we need to do is to convert the normalized propagation constant into the non-normalized one. So now equation D, yes, this is the challenge now. The whole idea, I am going to repeat equation D verbally. We are trying to reduce the thickness, and we are going to establish the first cutoff, the condition for the first cutoff that occurs. So let's establish the condition first. The higher the refractive index or higher the K number, uh, and higher attenuation constant, we are going to get the first cutoff. And as a result, using the formula given in equation 24, which is the formula for the cutoff, we can find this. And assuming that the frequency is not going to change, so lambda is 1 micron, and instead we change the thickness, reduce it, and we are trying to use this way to establish the cutoff, the first cutoff. M equals to 0 should be rejected because there will be no more, this is not the largest thickness. Now we are going to look at TE1 mode, and with TE1 mode we end up with a thickness 0.61 for the cutoff. Now we turn our attention to TM1 mode, and we find out the thickness is going to be 0.69. So this thickness is going to be larger among these two modes, TM and TE mode. So in this case, we conclude that the first cutoff is going to be the largest one first. As the thickness is reduced, then we find the next largest thickness, which is this one, 0.69 micron, as the first cutoff that occurs. Okay, thank you. If you have any question, please leave your question to the comment section of this video. Bye-bye.